the organizers for inviting us to speak today. We're presenting work that we did together with Luca, Peter, David, and David. And specifically, we'll be presenting results from our numerical studies of the conformal bootstrap of mixed correlators of fermions and scalars in 3D. And so this work comes as something of a culmination of many years of work by several of us in developing the technology of the conformal bootstrap. Notably, these papers here developed the theory, the algorithm, and then finally the software, Blocks 3D. So this work is the first major application of Blocks 3D. Hopefully that's only slightly cut off in the camera. So Blocks 3D makes it so that we can straightforwardly study correlators with spinning external operators of arbitrary external spins, and takes what would have been wildly impractical in the past, using sort of very ad hoc methods to construct your spinning crossing equations, and makes it practical. And so we are hoping to show how that works and how straightforward that can be. And so specifically, we are our first target for this new Blocks 3D paradigm. We decided to target revisit the Gross-Neveu-Yukawa GNY bootstrap that was done in these papers by Kos, Bufu, Jacobi, and some of us. And so let's see. And in those works, the authors studied just a single just correlators of just fermions without scalars mixing, and they were able to find a family of kinks that seemed to correspond to what in the literature was deemed the ON GNY models. So they found kinks, and so we set out to tie up some loose threads and find an archipelago. And then finally, one more thread that's worth mentioning is the n=1 member of this family, the ON-GNY archipelago, corresponds to the curly n=1 super Ising model. So super Ising. And this has been studied extremely thoroughly by Rong, Su, Avnasov, Hillman, Poland. Most recently, earlier this year, making a pretty kind of shocking determination of, shockingly precise determination of all the various CFG data. And so obviously we don't need to necessarily look for precision in that way, but there are still some interesting questions one might ask regarding supersymmetry without having to assume supersymmetry. So with all those preliminary remarks out of the way, I'll give you a brief outline of the rest of the talk. Aike will walk us through the more technical details of how we, what exactly we're studying, how we studied it. Then we'll bring the projector down, show off our results. Then the projector will go back up, and I'll talk a little bit more about some subtleties about this model we studied and clear up some confusions. And then we'll wrap. So hopefully there are any questions already, but if not. Okay, take it away.
Okay. Thank you, Rajeev, for the introduction. Okay, so the model of interest here is in 2+1D, the GNY, the Gross-Neveu-Yukawa models with some real two-component Majorana fermions interacting with a real pseudoscalar. Where the pseudoscalar possesses its own quartic interaction, as usual. And the symmetries of our theories include ON global symmetry, where the and Marana fermions transform it in the ON vector representation. And the pseudoscalar itself is an ON singlet. And we also demand that the theory is invariant under parity transformation, where the fermion is parity even, and the pseudoscalar, of course, is parity odd. And okay, so so for this model, as we tune the parameters of the mass term, and when this mass term, the coefficient of the mass term becomes negative, then the pseudoscalar pick up a width, and dynamically give mass to the fermion operators. And okay, and at the particularity, the sigma squared is only relevant operators at the fixed point. So yes, so that's a model, and we're going to bootstrap with the fermion operator and the pseudoscalars plus the relevant operator epsilon equals identified with sigma squared, which is parity even. And okay, so with those three operators, we'll first write down all the correlation functions, or all the 4-point functions involved in the system. And so this just the single operators correlation functions, and then like the mixed ones with permutations, and so this is fermion mixed with this, the pseudoscalar, and the fermion with epsilon, and sigma with epsilon, and finally the fully mixed operators with all three operators. Sorry, the fully mixed correlators with all three operators. And so, as you can see, this is a huge system, and because as we are studying non-scalar operators, some of the correlators pick up they can be expanded into linear combinations of different conformal tensor structures, and in particular, since we have conformal structure and also global symmetry, so that tensor structures, let's see, we can write them out as the functions times the tensor structures, which include the ON symmetries structures and also the conformal structures. So with all this taken into considerations, we have 38 crossing equations in total. And so the old way will be writing out huge, gigantic systems of equations. But now, as Rajeev mentioned, with some recent software development, in particular, it's a package called Hyperion Bootstrap, and also the Block 3D. The process of writing down all the crossing equations and expanding into blocks become much more systematically simplified.
I have a question. What is this Hyperion? Has this been published or is this unpublished?
It's publicly accessible.
But what does it do for you?
So it's so I'll show an example where Hyperion goes into the workflow. Yes, exactly. Let me just, as an illustration, do a simple example of what Hyperion does and how the information is passed into the software. Okay, so let me do examples with psi mixed with pseudoscalar sigma. Okay, so in this case, the flavor structure is rather trivial, which is just Aike. And so as for the conformal structures, we follow a previous work, this one you could do, counting conformal correlator paper. That gives a systematic way of writing conformally invariant conformal structures. So, and essentially it's iterating through the spins at the of the operators. And so for this one, we just operators and then the spin down, it's the same thing. I will omit those components for now. Okay, and so this is just a simple way of iterating through. And doing crossing, exchanging the first and the third operators. Sorry. And repeating the process, just then it's have the scalars at the first and the last. And because we exchange the x1 and f3 swaps positions, so
Do you want to write the other correlator?
I'll
Okay.
include it. Yes. So then, again, well, there's a second term, but I'm not writing down now. Again, following the previous papers, we can relate these two spin structures by permuting the spins, and as we do that, we can pick up some factors of -1s, and so we can rewrite. So rewrite it as the same form as above, and then doing the equating these two expressions, and by collecting this is a factor, and collecting the terms in front of the same structures. This is a form of crossing equations we obtained from this process. Okay, so this one particular holds some factors, -1, and the second function. Sorry, this is over here. Okay, and so for this mixing, so we have another permutation, which is putting psi, and sigma, but similarly we can produce a crossing equation like this. And so these crossing equations are what we put into Hyperion. And furthermore, as we do Bootstrap, we expand this functions into conformal blocks. And my pen is not so good. I think I can erase those.
So I don't understand. You have to derive by hand the crossing equations, and then you have to type them into some form that Hyperion is able to read?
Yes, so those equations basically what's involved is entered into Hyperion.
This is the form that goes directly into Hyperion. Hyperion reads exactly this.
Yes, and another set of information Hyperion takes is OPE channels.
Sorry, so does it automatically interface, for example, with blocks 3D, or do you need to do some gluing there?
Yeah.
It's automatic?
Yeah, automatic. Certainly you could do this without Hyperion.
No, yeah, obviously.
so this is what block 3D calculates. Block. It's a 3D blocks for arbitrary things. And the Hyperion also takes the OPE channels, and we need to define those. Again, as following the 4-point functions and same routines, we found the structures for the 3-point functions, and we need to define those channels. And so Hyperion takes these channels and these crossing equations, and then it split out the large 38 crossing equations involving matrices of conformal blocks. Yes. It's a systematic way that also automatic ways to produce crossing equations, and it's much more convenient when the system gets way too large. Okay.
And also in our system, there are 13 unique OPE channels that you have to keep track of.
Okay. So that's the routine to use to software. And then after we coded those elements up, the final input to the Bootstrap study is just the gap assumptions. And so yes, so our external operators, sigma, epsilon, and psi, which then we allow them to, we allow the scaling dimension of them to vary freely. And so there are several gap assumptions we put into the Bootstrap program, and one of the most important one is the parity of ON vector and fermion channel, which we call chi-I. So this gap, this sector is important as because of the equation of motion we obtained from the Lagrangian, which is so I can see that's this operator, the sigma times psi, which is supposed to be the lowest lying operators in this sector, is now a descendant. So that motivates us to put a large gap on this on the parity of ON fermion sector. And our gap is 3.5 on chi-I. And the second very important gap we have is in the hybrid odd scalar sector, which it's a we call it sigma prime, which is identified with sigma to the third power. And this gap is rather contentious, and the number 3 is well motivated in from the Lagrangian expansions. So the Lagrangian estimate is the first order is positive, is 3 plus first order is positive, but the second order becomes negative. So it's well motivated for large when n is large, but less justifiable when n gets smaller. However, from a previous study of n equals 1 superizing Bootstrap, the gap on this sector is greater than 2.88. So we still think that number 3 is a justifiable gap to put in our study. But at the same time, the next phase of this project, which is carried by Matt Harry, Michelle. It was using the navigator functions to explore how much we can lower this this constraint. Okay.
So for n equals 1, you expect that you should relax this constraint.
Yes.
Yes, we'll get to our n equals 1 studies. There are special cases.
Yes.
Sorry, but in the epsilon expansion, people have calculated this Lagrange onto some loop order. Did you try playing around with it?
Yes.
Like the most generic Lagrangian that you can write down has been written to some amount of loops, and from that you can extract the scaling dimension of sigma 3.
Yeah.
And it agrees with this, or?
Yes. No, this is there's some subtleties in the epsilon expansion which we'll come back to.
Right. And there's two other gap assumptions, but there are three other gap assumptions. One is epsilon prime, which is second lowest line in the parity even scalar sector. And as I mentioned at the beginning, the sigma square is only relevant operators at the fixed point. So we put a lower bound 3 on this sector. And the two others, the second lowest line fermions, and also a scalar transforming the symmetric tensor representation. So those two gaps are rather moderate, inspired from the perturbated calculation.
I'm just copying it. Sorry, what about the side operator?
Side operators, that's
Isn't that the same sector as sigma prime? So that is the equation of motion eliminates that. So if you consider the sigma equation of motion, this ends up becoming a descendant. Or this rather not that specifically, but a linear combination of this and phi cubed. So sigma cubed. So this and this actually just become one operator. Good.
we should read down the slides.
Yes. So are there any more questions about our setup? Because once we bring the projector down, it's harder to answer. Let's go.
Rajeev, just watch out for when it goes under, so that it doesn't bring down the.
Yeah.
Maybe pull it up towards you. Pull it a bit. It's
Oh.
okay. It's fine. It's fine. No, it's okay. It's okay. You can. It's just for you
Pull
to
it towards
reduce.
you. Yeah.
It's fine.
Oh, okay, yes. So we're scanning three-dimensional space in scaling dimensions, and accompanied with OPE scans. Yeah, this is the previous work by just bootstrapping the purely fermionic correlators, and so the paper reported a series of kinks down here, which agrees rather well with the perturbative calculation. And this is our result, projected in the same thing as the previous fermionic bootstrap. So in delta sigma and delta psi, and yes, so we studied n equals to 1, 2, 4, and 8, and those are islands we obtained.
I should say the n equals 1 is not actually our own bounds for n equals 1 here. We just plotted the previous result from the supervising.
So the dotted line here is Argand calculations, and as you can see, it agrees well or better as n becomes large, but relatively not so when n decreases.
It's amazing.
Thank you.
Yeah, it was quite difficult to make a plot that didn't make these look like, you know, dust on the projector or something.
Okay, and so this is the other projections into delta epsilon and delta sigma plane. And this big region here is the icing bootstrap with the same bound on sigma prime. And yeah, well, n equals 1 lies outside of it because it has a different bound on this operator.
So you found theories which populate the continents.
Yes, it is a compound.
Okay.
And the Ising bound is a subset of our crossing equations. So.
Okay, so this is zoom in. Those are zoom in figures for n equals to 2 compared with the previous studies of epsilon expansions and Monte Carlo studies. So, well, in the figures on the left, it's clear that we achieved order of magnitude improvement on the bound.
So on the figure on the left, the error on delta sigma is extremely small and much smaller than epsilon expansion Monte Carlo. But on the figure on the right, somehow the error on delta sigma is not as small.
What is going on there? It's a little bit hard to see the way that this is made. Also, these islands are projections from higher dimensional island.
Yeah, but the projection,
Yeah.
the size, the delta sigma size should be the same as well.
Are you saying Monte Carlo is excluded by your bounds?
Yes.
So, I mean, is there a reason why Monte Carlo is
Oh,
harder to
Well, so I should say these Monte Carlo error bars are, well, they're at 1 standard deviation. So, you know, there could be a few standard deviations off from them.
Is there some intuition why Monte Carlo is worse for this model than like?
Shai, before we discuss the worst, I'd like to understand so the size of delta sigma error bar. On the plot on the left, I see that the delta sigma error bar that you get, for example, is
65 to 66.
a factor 5 smaller than the vertical size of the yellow cross. At least. While on the right plot, it's no longer, at least it is factor 5.
Yes, yes. Yes. So this is islands that we present are the sort of non-rigorous island estimates that you get from taking the so in this Jelani search scheme, you end up with some set of simplices, and what we did here is we projected the points down and then chose the centroids of all the points. And so if you have a simplex which is, so I should say that we did the projection before the mesh in this case. We didn't project the mesh itself down, so the Jelani mesh itself is different between the two, and so this is sort of for the purpose of visualization. The numbers we report in our upcoming work are determined from the 3D mesh and not the 2D mesh. So this is just sort of for the sake of visualization. That's why you can get funny parts.
That doesn't explain why the islands are so different.
Yeah.
You should be projecting in delta sigma. They should be, if you project both plots in delta sigma, it should be the same projection.
Yeah.
So, what's it?
I don't have a great answer to that, unfortunately. I should say the n equals 2 searches that we did suffered from some kind of low statistics, let's say, because we ran out of computing resources. Yes.
Okay, you need to
Yeah.
sorry, you need to fix this.
Yeah, I agree.
Well, so I just have, I mean, After all these things are fixed, are you expecting Monte Carlo will now overlap with your islands, or is that not clear?
So we can show you the numerical result at the end. Do you want to jump to that table straight away? Yeah. So these are now the actual rigorous estimates that we've made. You can see for yourself.
What's this B-Rex 3?
That will be explained later. But yeah, the epsilon still does not intersect with epsilon, delta epsilon. Oh, sorry, the delta epsilon estimates still don't intersect with Monte Carlo, but the delta psi estimates now do. And
So I mean, I'm just wondering, like, so in other bootstrap studies, say ON model, usually Monte Carlo's always matches bootstrap, maybe bootstrap more precise. Is there some intuition why Monte Carlo might be worse for these
Yes.
theories?
yes, and that's also something that we will discuss later when the projector goes
Oh, I
up.
see.
Fermions. Let me go back to the fermions, yes.
This is n equals to 2.
Are there any more questions about n equals 2?
So n equals to 4, well, we put a star on the Monte Carlo calculation here, which you will also explain later. It's a long story. So for this estimate, the Monte Carlo study does not produce any predictions in delta psi scaling dimension. So finally, similar story with n equals to 8. And
Yes,
another
and then
this is surprising.
yes. So this is now, as I said, n equals 1 is a special case. N equals 1, we believe, is the n equals 1 GNY model is just the super Ising model, we think. And again, this has been studied to a great deal, but one question you might ask is what do you get if you just don't assume supersymmetry, just assume a fairly conservative set of gaps, and do the same procedure that we did in the other islands. So yes, as Slava pointed out, we've loosened the assumptions here. So sigma prime is just greater than 2.5. And so plotted here are two separate islands, one done with a derivative order n max equals 6, which is big lambda equals 11, and n max equals 10, which is big lambda equals 19, and projected onto these same sets of axes. This line here is the relation you'd expect from supersymmetry. Sigma equals delta psi minus 1/2. And delta epsilon equals delta sigma plus 1. And the kind of remarkable thing is that the island is rather big, but the tip coincides exactly with the supersymmetry constraint, and then under different numbers of derivative orders, the tail seems to shrink very heavily, but the tip is persistent. So that's maybe a bit vague, but what we then did is, I don't have a visualization for this, unfortunately, but we took the supersymmetric point right there, and we binary searched along this line with just our conservative assumptions. And along this line, we get that delta sigma equals 0.584448. So in other words, we have it determined to 3 or 4 decimal places. And the point of comparison here is the supersymmetric bootstrap, which at nmax equals 30 with all the supersymmetry constraints, but without spinning operators, they got 0.58443583. So about an order of magnitude better with all the supersymmetry information plugged in, along with isolating the sigma prime operator, the second parity odd scalar.
Do
But
you scan over scale over OB ratios or the scale dimensions?
sorry,
In this work, do you also scan over OB
Yes.
coefficient?
yes, we do.
Which one?
We scan over the. Let me find a good place to put it. We scan over
Well, let me put it another way.
Yeah.
What dimensional is your scan?
seven
Seven.
dimensional. Or six. Not seven. Six. So we scan over the ratios of psi sigma, psi epsilon, sigma epsilon, and epsilon. So that's three ratios along with the three external dimensions. Another thing to say is that this is
With the ratios of bigger, you don't scan, you presumably use the cutting surface over.
exactly the cutting surface of it. That's what we mean. So this is at nmax equals 30. This was at nmax equals 10. But it's different size system, so it's not exactly apples to apples. Yes, this is also fairly comparable to some of the earlier works here.
Sorry.
Yep.
When you do this cutting surface algorithm, do you have some bounding box for these OP ratios? Or can you
Yes, but it's always like a very sort of conservative box that was previously excluded at a lower nmax. So the point is just to keep it from running away. And so one more thing to say here is that this was with a fairly conservative set of gaps, specifically delta sigma prime being greater than 2.5. But one thing that we tested very briefly before putting it away, because there are other more important things to be doing, we found that the tail here is extremely sensitive to this 2.8 gap, and this is related to something that Alex, Aaron, and David found in their supersymmetric bootstrap. By applying a delta sigma prime gap, they're able to bring the tail of basically exactly this way in. So, yes.
So did you search along that line, like one line at a time, or did you just impose both relations?
We impose both relations, yeah. So this is a projection of both lines. So we scan over both. So it's a one-dimensional.
So that led to that number.
Sorry?
That
Oh, sorry.
procedure led to that estimate of scaling average.
Yes, precisely. Yeah. So you might ask now, okay, well, we seem to be, if we take the minimal supersymmetry constraints, we seem to get results that are comparable, maybe an order of magnitude wider than the complete supersymmetric bootstrap. But one might ask now, instead of just looking at the scaling dimensions, is there some other way to see that there's some supersymmetry going on here without imposing it? And one of the great things about having the setup for fermion scalar mixing is that we have access to half-integer operators in our crossing equations. So, more specifically, if there is supersymmetry going on, you would expect a supercurrent to live at the unitarity bound in the spin 3/2 sector, in the spin 3/2 parity odd sector. So what we did is, see this orange line here? We took a line that interpolated between this, the supersymmetric point through the center of this island to the end of the island. The line is written very large, but we just took the nmax equals 10 island. And we sampled points along it, and we looked to see what the maximal gap in this supercurrent sector we could impose without making the points disallowed. And so this orange line here this orange dashed line right here is the supersymmetric point, the tip of the island. And this is the tail out here. And what we found is that throughout the entire island, the maximal supercurrent gap you can apply without getting rid of the whole island, so in other words, where we think this quasi-supercurrent would be living, it has to be less than 2.54 or so at mx equals 10. And more specifically, at this, at the supersymmetric point, we specifically got that the supercurrent lives at, well, there's an operator in this channel that's important to this CFT that's at 2.50003 at mx equals 14.
Rajeev, aren't you beating a little bit a dead horse here? We know that the supersymmetric CFT exists. We know that n equal 1 exists. So what precisely, which scenario are you trying to exclude here?
Well, so this is a sort of a bootstrappy proof that you need to, a non-perturbative proof, if you will, that you have to have, that this island has to have something that looks like supersymmetry. And I'm not aware of there being this kind of like a proof.
But there was already a bootstrap proof that the supersymmetric CFT exists.
Yes.
So, barring the possibility of having two CFTs.
Precisely. It could, maybe there's another CFT that lives right in there, and but who knows? But also maybe you can consider this as a proof of concept for proving other sorts of theories using this sort of an approach of scattering out the supercurrent.
Well, at least you can use this as a consistency check that, you know, what we're doing is not completely wrong.
Yes,
but
also
it
that.
uses things that we already knew.
Also that.
I mean, it's interesting that some gap condition forces supersymmetry on you. There are people who believe that unitary CFTs with semi-classical ACS dual will have to have supersymmetry. I mean, you know, maybe this can be generalized to large entity.
No. Okay. Great. And next is just the table. So, and then this is just what we showed earlier as well. Just take another look if you'd like. Yes.
Which one of these models is particularly chronologically interesting?
That's a very good question that I'm going to get to once the projector goes up.
Are you giving the entire talk or should you speak sometimes?
Not much.
Sorry, then.
Ask any last minute questions? Are there any last minute questions before the projector goes up?
Maybe, how serious was this Monte Carlo study? Because you quoted, I think, Monte Carlo studies said the Bootstrap did way better, but the Monte Carlo study was maybe not that serious.
These were pretty serious. These were, cited in the top reviews of the reviews that we referred to. These were, in particular, the n equals 2 Monte Carlo study quoted the previous controlled bootstrap results. So, probably fair to be there.
What was the question? Were they serious people or how hard they tried?
How hard did they try? Well, both, I guess.
I don't know, it's hard to tell.
Yeah. What was the system size? That's a good question. Not sure. I can show you the reference.
But you put some people out of job.
Well, maybe. Yeah. Okay. Projector is going up.
Need to press it again.
Okay. Okay, so now as to the question of which of these are phenomenologically interesting, there are some some things to say. So, one thing to note is that for the n equals 1 case, as we said, it coincides with the super Ising model. We expect this to be realized actually, as Max mentioned earlier in the week, it's realized on the surface of, expected to be realized on the surface of helium-3b as a phase transition, and right, so as part of a certain phase transition. The phase transition actually is true for any n, not just n equals 1. And it's the phase transition between class D3 to class D topological superconductor in 2 plus 1 D.
What do you tune to reach this phase transition?
Sorry?
What do you tune to reach this phase transition?
It's to tune this.
No, I mean in
yeah.
helium-3b.
In helium-3b, I don't know. I'm not an experimentalist, unfortunately.
No, it's not an experimental question, sorry.
This is if you'd like to read more about the helium-3b, this is mentioned in the following reference, so which I could read and get back to you on that question.
Sorry, I'm total chemistry dumbass. Is B here boron or some description of the thingy?
Yeah, it's called the B phase.
Okay, B phase.
So, yes. So, and then, right. And so specifically, this transition. Let's be a little more specific about this. What happens is the class D3 is the class of time reversal preserving Majorana fermions, in other words, massless Majorana fermions. And when at the critical point, the VEV of sigma breaks parity, but also breaks time reversal symmetry, and therefore breaks the theory to class D. This is something that is sort of very new to me, new to us, in terms of what all this means. So if anyone has any thoughts about this, I'd love to talk afterwards. But something I can say is that when people typically study these theories of fermions and scalars with a Yukawa type coupling, they typically study so-called chiral Ising universality class, which has the following Lagrangian, and it's quite similar, but it is distinct. So let's write that out. Okay. So in this theory, there are, instead of having a single family of n real two-component Majoranas, you instead have two families of these Majoranas. So real two-component Majoranas, and they're distinguished by the sign on their Yukawa coupling to the scalar. And you still have the scalar. Okay. So, right, so the, so this is, one thing to also be aware of is sometimes people will write this, instead of in two-component notation, while still being in 2 plus 1D, they will write this in 4-component notation. They will repackage these pairs of Majoranas into 4-component operators. which leads to some of the confusion between these two theories, but that's why we'll...
Is it gamma 5 there or
No,
no?
no gamma 5.
So this is so they use 4-component 3-dimensional gamma matrices, which there is a whole lot of representations, and somehow they choose one particular, which is the one which you can complete to the 4D representation. It has to do with the 4 minus epsilon expansion. So in terms of that representation, this thing has a minus sign.
Yeah. So let's talk about the symmetries. So in our old theory, we had n real Majoranas, we had On. In this case, because we have two sets of n over 2 Majoranas, we have n over 2 squared symmetry, where acting on the Majoranas independently, and under which the scalar is still a singlet. Separately, there is a so-called chiral transformation, which is a Z2 symmetry transformation that exchanges the left and right families of fermions and also changes the sign on the scalar. So swap these, flip the sign on that. The Lagrangian is still invariant under that. This is called a chiral transformation, but of course in 2+1D there is no space-time chirality. This is just another flavor symmetry. Finally, there is a parity that is conserved, which is defined as follows. Is in the same as in this case, the fermion bilinears change sign, the kinetic terms are left invariant, but also the left and right are exchanged, and this time the scalar is left as it is. So the scalar is even under parity in this case. And, okay. So what happens when sigma picks up a vev is that the fermions get a mass, but they get masses of opposite signs. And by picking up masses of opposite signs, you break this one, the chiral symmetry. But your O(n)/2 squared symmetry and your parity are preserved, and therefore also your time reversal is preserved. So that is the main point of contrast between these two theories from a symmetry perspective. In this case, you're breaking parity and time reversal. In this case, you're breaking this flavor symmetry and preserving parity and time reversal. Okay, and this is why we believe, just by looking at the symmetries, that these are quite distinct. Also, the full global symmetry group of this can be written as O(n)/2 squared semi-direct Z2, whereas in this case, the full flavor group is just O(n).
Sorry, what's the suffix y parity accept way? If I combine it with scalar above, I can also look like define parity.
Sure.
In a way that sends things up to minus sigma.
Oh, sure.
But from the Lagrangian, you're not forced, right, to choose that for parity.
Of course not, yeah. So the composition of these is also a parity you would choose.
And that would be broken by...
That is also broken.
And so what? Then why is one related time reversal preserving and the other not? I mean, why should I believe that there is something physical about the difference in parity breaking here?
So the point is that in this theory, once you get to the symmetry broken regime, there's still a parity that you can construct. Whereas in this case, once you're in the symmetry broken phase, there's no parity that could be preserved. So that's a very good question. So, okay. So why have we belabored the difference between these two theories? Well, as we said, this is these can be confused for each other, and part of the confusion has to do with the fact that there's some technical challenges that make it so that different people studying different things will end up studying this either by choice or sort of by accident. And so for
Sorry, are they believed to have the same fixed point or no?
Yes, so that's a good question. So people believed that for a while that these, there was some supposition that these could have the same fixed point, but I'll give some evidence in a minute that they are different.
Second question, which one is the one that people use in the epsilon expansion?
There's subtlety, I'll get to that. Yeah. So let me just very quickly talk about the Monte Carlo people first. So for Monte Carlo, the parity, the parity breaking here, the parity anomaly, and the time reversal symmetry breaking makes it so that the theory on the left suffers from a sign problem, which is not insurmountable, but definitely presents a challenge. And as a result, 2 out of 3 of the Monte Carlo studies that we cited studied this theory instead, because this theory doesn't suffer from the same sign problem. So the n equals 2 Monte Carlo that we cited is on the left, and then the n equals 4 and 8 are actually for this theory, which is why we put the asterisk on the Monte Carlo studies. Sign. Separately,
So you're saying you don't believe the arguments that actually that's a legit thing to do?
to study this as a way of studying this?
Yeah.
Yes, we don't believe that. And so the evidence for that comes actually from this story that I'm going to say about the epsilon expansion, which is the epsilon expansion. If you're starting in 4 dimensions, you might write a coupling that looks like this. You will be studying a theory with this coupling. And so as a result, so basically spinors are hard, but
I would say the main evidence for solid expansion is actually for large n expansion.
yes.
But
What about the large n expansion? What about the large n expansion?
I think that's more convincing evidence that the fixed points
Yes.
are different. So.
Yes. Yeah, we'll also talk about the large n. So in the epsilon expansion, people had studied the epsilon expansion to 1, 2 loops, and they found that in the n equals 1 case, which as we say has supersymmetry, that their epsilon expansion results were consistent with supersymmetry. Then they went to 3 loops, still consistent. At 4 loops, the following group, which I'll write down, they found that they were slightly inconsistent with supersymmetry when n equals 1. And they looked over their work and they did their epsilon expansion more carefully through some scheme that they refer to as dreg3. This is what the dreg3 was in that plot. And they were able to recover supersymmetry. So in particular, they found some diagrams at 4-loop order which are actually different between these 2 theories. And so in the epsilon expansion, they found that without realizing it, I guess, in exactly these terms, they found that these 2 theories are exactly different. And the difference between them is 2 times 10 to the -6 in the scaling dimensions at 4-loop order in this epsilon expansion. And we were able to get this. Number thanks to Michael Scherer, who we've been in correspondence with, one of the authors of this paper, who was kind enough to give us these scaling dimensions.
So you say when you do epsilon expansion, you are forced to work with that formulation if you don't do anything special?
Yes.
Well, I think, at least to me, it's unclear because epsilon expansion you're doing with experiments, and then you have to come up with all these rules for gamma matrices. And they were using some sort of rules for spinors in epsilon expansion, and they found this disagreement. They found that the supersymmetry is not preserved. And then my understanding is that they saw, okay, if you actually make this couple of diagrams not vanish as they vanish with current rules, then you restore supersymmetry. And then we came up with some ad hoc rule to tweak which they don't have. I don't think they have a systematic procedure to all orders in epsilon how to preserve supersymmetry. They just said that this first order where it's broken, you can make this ad hoc fix to the three spinors, and then you restore the n equals 1 supersymmetry. So that's exactly.
I'll give the diagrams now. So if you have a diagram that looks like this, where you have a scalar here and two fermions coming out here, this appears in the beta function, which therefore affects the CFT data. This diagram has a loop with an odd number of vertices, and this appears both in large N expansion and in the epsilon expansion. In the large N expansion, in particular, the correction to delta sigma, it appears at 1 over n cubed order. And with the odd number of vertices, if there's no sign difference, it doesn't vanish. But there is a sign difference between coupling between the species of fermions, then this diagram vanishes and doesn't appear as part of the perturbative calculations of this theory.
And it's very clear in large N, because large N you don't have to invent any magic with spinors. But
Yes.
when we talk about epsilon expansions,
Yes,
like,
yes.
it's more confusing what
Yes,
the
yes.
processor is going on.
So if you
So sorry, the issue was how the spinors were being repackaged when going from D equals 4 to D equals 3. Is this the statement?
yes, yes.
And there was a diagram that in the one case vanished and in the other doesn't, and when it doesn't vanish, you get the supersymmetry. Is that what they're claiming?
Yes.
Yes.
Okay.
But it's very ad hoc. It's just
Yeah,
like,
yeah.
just
Sure,
this
sure,
is-
yeah,
Yeah, as Peter says, it's a bit clearer with the large N expansion. You don't need to worry about doing some weird dimensional things. It's just simply true that if you do the large N expansion to 1 over n cubed order, you'll find these diagrams which vanish in this theory and don't vanish in the other theory.
One more question. In large N, you don't need to use spinors then, or how does this get?
You just natively use three-dimensional two-component spinners, so you don't need to worry
Okay,
about
yeah.
the
Good.
So yes. Yes, so as a result, so this is perturbative evidence as to the fact that these are different theories. And so this is, maybe we can make the somewhat strong, we can make a statement that the super Ising model is not a member of the chiral Ising universality class, which has often been said. So,
But if this is the case, so suppose that we don't, n equal 1 is a special case, because in this case the right theory is not even, I don't, you have this O1 half curve. Suppose we take n equal 2. Then suppose we are saying that these two theories have to be really close to each other. They both exist. And so what does this mean? Does it mean that there is some operator which you can turn on in this theory, which is going to break the symmetry from O2 to this? So is the story somewhat similar to like OAN sits very close to the cubic model? Is there some very, very close to marginality operator which will arrange a flow from one theory to the other?
no, and so but part of that is, so part of the other superficial similarity comes from the fact that we called this one sigma and that one also sigma. But these are actually distinct operators, because specifically this sigma. Are you asking, is there a way to break ON down to ON?
Yeah,
to
by turning on some operator.
Yeah. So that's not possible because sigma here is a singlet under ON. It does not see ON at all. Whereas in this theory, so you need the Z2 to come from the ON. The Z2 would be a subgroup of ON. And this sigma does see the Z2. So.
But then it's really unexplainable from the RG point of view. You're saying there are two theories. They have different symmetries.
Yep.
And they are sitting extremely close to each other in all scaling dimensions.
Yes.
And you cannot arrange for an RG flow from one to the other. That's really.
Well, they have different symmetry groups, and
But one is a subgroup of the other.
yes, one is a suburb of the other, but the lowest, like if you look at the lowest dimensional scalar operators, their representation, like you cannot embed one subgroup, like this ON over 2 squared, some product Z2 into ON, in a way which also would respect the representation of these groups on the lowest dimensional scalar operators. So in one theory, in ON theory, you see that there is a group ON and there is a very relatively low dimensional scalar sigma, such that ON acts trivially on sigma. The other theory, you have this ON over 2 squared semi-product Z2, which is a subgroup of ON, but you see that there is a light scalar in which the 2 acts by change of sign.
But you are looking at Lagrangian, but what if I look at some other operator? What if I think it
That's
has
why I'm
a
trying to
CFT?
phrase it in a way which doesn't use Lagrangian. I'm just
Yeah.
saying there is a CFT and I'm looking at low-dimensional scalars.
Yeah.
So one theory has a scalar which is trivial under all global symmetries, and then the other does not.
So is the point that then, I mean, then the flow cannot be short because some operator which has the representation has to come down or something. I mean, there will be operators here, not so.
That's what it looks like. So here, it just seems some kind of coincidence that they say in 1 over n they differ at very high order, because this diagram that Rajeev wrote, you might ask, well, why can't you draw fewer lines between the two loops? And the answer is that if you remove 2 lines, then each loop will be trivial, because each loop is like a parity-rod scalar 3-point function, which doesn't exist. The parity-rod scalar 5-point function does exist in 5 dimensions. So this diagram is non-trivial only when you have quite a lot of loops. So it seems some kind of weird reason why they are close to each other to like large orders and all expansions, but then finally they're different theories. Not really close to each other in our G space in some sense.
I should say that this coincidence has confused people for probably 30 years. So we're in good company. But so these two we think are distinct, and one thing you might want to ask is, okay, what can the Bootstrap say about that? And one thing you should consider is, well, we don't expect these to ever really coincide because they don't satisfy each other's crossing equations, but you might check using the navigator to see if we can compare our bounds on scaling dimensions, and we're not quite at the 2 times 10 to the minus 6, but maybe we might be able to see something. And we actually have the right-hand system implemented already, though we haven't really done anything with it. This is a much more complicated system for the Bootstrap. This is 53 crossing equations with 20 OPE channels. So it's much more computationally expensive as a result. Are there any more questions about these two universal classes? Yeah.
What is the dimension of the operator psi 1 minus psi 2, psi 2? So that would be the operator which breaks O2 to the theory of the.
So in other words, this operator here.
Yeah.
You're asking about the N model.
Oh, N model, yeah.
So this would be in whatever
2 plus.
The spin 2 O1 spin 2 sigma t.
Yeah, it would be similar to sigma t, and so
Yeah, could it be close to marginality? Is there some? I know for sure that it's not close to marginality.
it would need like a pretty big positive correction, I suppose.
Well, I mean, I don't think we ran the bound on it actually. So.
No, yeah, we didn't run.
But so you don't know if that operator is close to marginality. Then by turning on that operator, you could arrange the flow from one theory to the other.
But it would also have to be close to marginality for, not just n equals 1, but
Yeah. For all n.
all n.
Yeah.
So
The large n
doesn't
not.
has dimension 2.
Yeah.
Large n has dimension 2.
Maybe we'll think about some kind of multi-critical point where you have 2 sigma fields, which could kind of, and then you have flows from that to either this or this. I don't know if that's.
Yeah, I mean, if you turn off both of these couplings, you get the same theory.
Suppose you have like sigma 1 and sigma 2,
Yeah.
which you tune both masses to zero, then maybe that multi-critical point you could maybe think as a mother or father of both of these theories, if you could. Otherwise, I don't
But
see-
also, yeah.
So, okay, I got a little bit lost. Did people do epsilon expansion computations for both Lagrangians?
Effectively, yes.
No, because the reason I'm asking this is because if the recipe for continuing the spinor down to d equals 3 is wrong, then maybe it shows up with this diagram. Maybe these two Lagrangians have the same fixed points, just one of the two computations is wrong that for loops.
Yeah, but that doesn't change the fact that the large n expansion is different.
The large n is correct, but the point is the large n doesn't agree with one of the two Lagrangians, right? That's the issue.
No, there is one large n expansion for one theory, and there is large n expansion for the other theory.
Oh, and these don't agree.
And then
Yes.
these are the
Oh,
theory.
okay,
Yes, yes.
okay, I see.
There is diagram which vanishes in
I see. Okay.
Any more questions about this one? Or should I wrap up?
But the point isn't necessarily at high order.
We can have two legit fixed ones that are extremely close. It seems so far.
So, yes, and so, yeah, so anyway, we have, regardless of this complication of these two models, we now have, a Bootstrap setup which can handle fermions and scalars, which, so one thing we might ask is, so I could mention that the sigma prime is a bit sketchy as a gap, so you might see how to study it, and as like I mentioned, Matt is hard at work to shore that up. But you might also consider what are some other spinning theories that you might want to consider that mix spinning operators with scalars or different kinds of spinning operators. So, for example, stress tensors with scalars, currents perhaps. And, but there's also a broader family of theories around this one, where if you have different symmetry groups acting on the scalar, different numbers of scalars, there are other physically interesting universality classes that certainly could be Bootstrap targets. So it seems like there's a lot of things we could be doing, and that's an exciting place to be. So thank you all. Questions?
Apart from this n equals 1 example, is there, which of these two models is relevant to any experiment, or is there one?
So there's not a lot of literature on this theory, due in part to these technical challenges that I mentioned, for that other methods might have some trouble with. There are, as I said, this sort of has a connection to this sort of topological phases of materials. I actually would like to talk to some people about it to see if we could figure some stuff out of it. There's much more.
This connection is for every n, right? Not
Yes,
just for
yeah.
n equals 1.
Yeah, this phase transition is true for any n, and it's not just n. And this theory has considerably more literature on it, and has connections to phases of graphene as well as some more actually. This breaks. By changing the parity, by going to this parity, you can say it's going to like class BDI, BD1. I don't know what the nomenclature is. Matt?
Yeah, so earlier you mentioned Hyperion, like, could you like summarize these steps from like just having a theory to actually solving a Bootstrap problem in Hyperion? Like, how does it compare to simple Boot, for example?
Well, I don't know what I could I haven't used simple boot myself, so I can't make an explicit comparison. But maybe. Okay. But since you went through the setup, you want to answer this one?
So the comparison.
Yeah, the stuff that we need for Hyperion.
Also, because I'm not familiar with other routines either, unfortunately. But so my own experience is like the process of producing the crossing equations is very simple. And, it's more just obtaining, calculating all the structures correctly and defining all the symmetries of the structures correctly. That's and the rest of it is rather automatic. And personally, I've never written down like 38 crossing equations expanded into blocks.
Yeah, the big thing is it's basically exactly what I showed on the board. We're not exaggerating when we say that it's basically just that. Throw it in the code. Call it a day.
Well, maybe I'm wrong, but one difference is that simple boot is probably only working with scalar equations.
Yes, but I think yes. In
Yeah,
simple
not
boot,
just it also supports the float city.
huh?
It also supports float city.
Oh, okay.
Just
Okay.
Okay. No, maybe.
So does the program take care of the structures of the local symmetry automatically, or do we still have to do this by funds? Like if you want to do a 4-point function of 4 vectors, Lorentz vectors, not global symmetry vectors. Do you still have to do that a bit by hand, or to sort out the tensor structures, the sum rules, etc., or is this automatic as well?
Okay, so what you need to do is you need to basically say that whether the 4-point functions and whether the crossing equations, the different components that is fine, Hyperion understands what are the 4-point structures for the 3-dimensional theory, so you don't have to worry about that. You just tell it what are the relations between different 4-point structures. And you also need to tell it what are the 3-point functions that you want to use. Also, it understands what are the possible 3-point structures for any 3-dimensional 3-point function, so you just tell it which particular linear combination to use. So like you need to figure out, for example, if you have identical operators, you need to tell it to use symmetric structures. It's not going to know that automatically. So you just input that information and then it does the rest. And the global symmetry structure you have to do by hand because there is no, like as far as we know, there is no libraries which just work for all, compute everything you want for all the groups, so we just didn't bother with that.
But it's sort of modular in the sense that once you write the ON graph theory for, say, ON vectors, actually this is what we did. We first implemented the ON vectors that are scalar operators, and then just took that whole clock and plugged it into the fermion 4-point functions. So.
Are there more questions?
Shai?
One last question, I guess, with the general. Are you guys trying to do this in like 4D for like general spinning guys?
Peter?
Well, in 4D, the status is that if you want to compute confirm blocks, you still need to work with weight shifting operators.
Well, I was just wondering, you guys like trying to do numerical bootstrap with like spinning 4-point functions?
Yes. That is being tried.
Obviously beyond spin 1 though.
Beyond. That is soon to be tried.